Hey everyone, and welcome. Have you ever taken a photo that looks amazing, totally sharp, but the second you try to post it or shrink it down, it just turns into a blocky, pixelated mess? Well, it turns out there's some really cool and surprisingly simple math going on behind the scenes. So let's dive in and uncover the secret that separates a perfect photo from a digital disaster. All right, we're going to kick things off with a problem that I am positive every single one of us has dealt with. You know the feeling. You have this great picture, you resize it, and suddenly it just looks, well, terrible. So you start with something like this, right? A beautiful, crisp photo of this dog on the left. But when you shrink it down, you can end up with this jagged, blocky catastrophe you see on the right. All that amazing detail is just gone. It looks totally broken.
And that brings up the big question, doesn't it? You're not adding anything new to the picture. You're just taking information away to make it smaller. So why in the world does it get so messed up in the process?
Well, the most obvious way to make a picture smaller is to, just throw away pixels. If you want to make it half the size, you could just delete every other row and every other column. Seems logical, right? But yeah, this is exactly where things start to go wrong. And check this out. This shows you precisely what's happening. As we keep shrinking this Van Gogh portrait using that simple toss out the pixels method, you can literally see it getting more and more jagged and distorted. This brute force approach just completely butchers the original image. So if just throwing away pixels is the wrong way to do it, what's the right way? Well, the key is to understand an image's hidden structure. We have to stop thinking of a picture as just a grid of dots and start seeing it in terms of frequencies. Okay, so every image is made up of what are called spatial frequencies. Now, think of it like this. Parts of the image with smooth, slow changes in color, like a nice soft sky, are low frequency. And the parts with really sharp, sudden changes, like the fine texture on the leaf or the pattern on a shirt, those are high frequency. All that fine detail lives in the high frequencies. And now we can finally put a name to the problem. It's called aliasing. It's that awful visual distortion that happens when those high-frequency details get all scrambled up when you resize the picture. When you just throw pixels away, you're sampling the image incorrectly, and you end up creating those ugly, blocky patterns that weren't even there to begin with. Okay, so if the sharp, high-frequency details are causing all the trouble, how do we fix it? Well, the solution is brilliant, and honestly, it's completely the opposite of what you'd expect.
Here it is. Get ready for this. To make a sharp, detailed image smaller without destroying it, the very first thing you have to do is make it a little blurry. I know, that sounds totally backwards, but trust me, this is the secret sauce.
So this process has a technical name, low-pass filtering. You're basically running the image through a filter that lets the smooth, low-frequency parts pass through, but it softens or it totally removes those high-frequency details that cause all that aliasing. You're getting rid of the problem before it has a chance to happen.
And the results, they speak for themselves. The dog on the left was gently blurred or low-pass filtered before it was shrunk down. The dog on the right was not. The difference is just, it's everything, right? One looks great, the other looks like a mess.
So how do programs like Photoshop actually do this magic blurring step? The answer is this little master tool, a tiny grid of numbers with a really cool name. The whole operation is called convolution, and the tool it uses is a small grid of numbers called a kernel. Just think of the kernel as a recipe. It slides across every single pixel in the image and tells it how to change its own value based on the pixels right next to it. This slide actually breaks down how it works. See, the kernel just slides over a pixel and its neighbors. Then it does some quick multiplication and addition. It's essentially creating a weighted average of that pixel and all the pixels around it. That's what gives us that gentle blurring effect we need. It's just simple math. And here you can see the whole thing in action. On the left, that's our result, the slightly blurred, filtered dog, ready for resizing. And on the right, that's a little snippet of Python code that makes it happen. You can see the kernel being defined and the convolution being run. It's the perfect link between that simple math and the polished final image. And this is where it gets really powerful. This whole process isn't just for blurring pictures to resize them. This one simple tool unlocks an entire universe of photo effects. So the main takeaway here is that the mathematical process, the convolution, it never changes. It's always the same. The only thing that's different are the numbers inside that tiny little kernel. By changing the recipe, you completely change the outcome. For example, If you use a kernel with a big positive number in the middle and negative numbers around it, you're not blurring anymore. Now you're exaggerating the difference between a pixel and its neighbors. And the result? A sharpening effect that makes all the details just pop. And of course, if we use a kernel that gives equal positive weight to all its neighbors, well, you get that nice smoothing or blurring effect that we started with. Same process, just a different kernel. In fact, just by swapping out that tiny grid of numbers, you can smooth, sharpen, blur, enhance details, intensify colors. You can even do crazy things like detect the edges of objects in a photograph. It all comes from one core mathematical idea. Which brings us to a final, pretty mind-blowing thought. All of these powerful effects, they come from applying just one kernel, one simple filter. So it makes you wonder, if one filter can do all of this, what could a whole series of them, stacked one after another, be capable of? And that question, well, that takes us right to the cutting edge of modern computer vision and AI. Thanks for watching.